So the idea behind least squares is we want to find a model for a set of data. So given a set of data, what line best fits the data? What's the line of best fit? What is the best way to describe this data with a line? So we can see that there's a lot of ways that we could build a line. If we think in terms of just elementary algebra, then 2 points determine a line. And as we can see, this collection of points is not going to fit on one line. But do I use this line? This line looks like it undercuts too much of the data. This line up here, between those 2 points, let me draw it from this side. This line up here, that's also seems to be a bad fit. Maybe these 4, but then there's like, these 4 are kind of roughly on the same line, but look how many points are off the line, and look how far away from the line they're going to be. Or is it in here? Maybe these 3? What's kind of the, or maybe these 4? A couple off. If we just start picking points at random, we could make some very bad decisions about what line fits. If I want to manipulate you with some data, I'll cherry pick my data, and I'll pull these 4 and say, oh, look, the trend is down. The trend is decreasing. Oh, wait, no, that's not the message that we want to send? Oh, okay, oh, the trend is increasing. We want to increase confidence, so it should increase faster. So I'll pick these 2. Although look how fast it's increasing. And there's like, well, what about all that stuff under the ruler? And you're like, well, ignore the stuff under the ruler. And then you turn to your assistant, like, oh, give me an opaque ruler, so they don't see all this stuff that I'm ignoring. Right? But look how bad these 3 points would model this data. So we can't just say eyeball it. It's somewhere in there. That's not precise. No mathematician is going to be like, oh, just eyeball it. Actually, mathematicians everywhere would just be like, oh, just eyeball it. But those mathematicians have a lot of experience with best fit lines. And if you really want to convince someone, it's like, well, let's define what we mean by best fit line so that our trend will make sense and we can justify its existence and not just wave our hands at the problem. So here's what we have to do. The least squares refers to the sum of the squares of the differences between a model line and the actual data. So we'll look at the sum of the squared differences. The least squares line So we're going to make the least squares line of all the lines that we could use to model this data. I'm just going to write them in this form. Of all the lines we can use to model this data, we want the sum of the squared differences between the line and the actual data to be minimum. We want to minimize the sum of the squared differences. So if I draw a line, I have to draw a line that has some room. I'm not sure that this is the least squares line, but I'm just going to say, let's look at this example. Not go so far. What we're looking, so there's a difference. Each of these data points, I've tried to pick a line that none of the data points were on, because we don't have to have any of the data sitting on this line. So each of these data points is off of the line. So for a particular value, say here at x1, there's an actual value, x1, say, oh, I shouldn't use x1. Oh, x1 is fine. Oh no, I used x1. Bollocks. say the actual data point is C1, and then there's an actual value, C1, C. You know what? I have to revamp this because I'm never going to be able to translate all these variables. My bad. Let's just go X and Y. I'm like, oh, dude, you were trying to simplify the problem. Why don't you simplify it? And then in my mind, I was like, oh, you'll be fine. Clearly, I won't be fine. So let's pick a point here. This is an actual data point, X1 and Y1. So there's a point X1, Y1. And then there's another point, let's say this point is going to be X2, Y2, and so on. So there's an actual point. There's an actual point X1 and Y1. And then there's what the line predicts. So here is a model. One of the uncountable infinity linear models. Then there's the linear model's prediction at this point. Something that stands out. Then there's going to be a predicted value. So if this linear model is, say, y equals mx plus b, we're going to take the value x1, plug it into our model to get a predicted value. And we do this for all those points. And what we're going to look for is the difference between those values. And what we're going to do is we're going to square the differences for each of the, we're going to evaluate the difference at each point. So find the difference between the actual value and the predicted value for each point. We're going to square the differences we'll talk about why we would want to do this in a minute. And then find the sum of the squared differences. Well, instead of say find, I want to minimize the sum of the squared differences. So that's the process. We have an actual data point and a predicted value. Then for each of those points, we want to find the difference between the actual value and the predicted value for each data point. Then we're going to square the differences, square all those differences, and then add them up. We want to minimize that sum. So the reason we want to square things, there's a couple reasons we want to square things. First of all, if there's, you see I have some lines, some points that are above the line and some points that are below the line. If I just said minimize the difference, there is some line out here through all these data points where the difference between the predicted value and the actual value, the sum is 0. And so there's some way that I could just draw a line with any slope, just kind of adjusting it up and down, whatever slope that you want. there's a way to get the differences, the sum of the differences, to be 0, because there's some positive and then there's some negative. So right now, the differences are all positive. The predicted value minus the actual value is positive. Or maybe I want to do it the other way around. The sum is all negative. If I just bring this up, I reduce that one to 0, but then these all other negative. And then this one goes along. And at some points, I'll be able to balance this out between this value and this value. That's just the theorem from calculus that says there's something in between. So if we square the differences, now all the differences are positive. And so now we're not going to be able to balance things out with an average, because once again, averages are terrible and we should try to avoid them all the time. So we want to square the differences. This makes all the differences positive. This makes all the differences positive. So now minimizing the sum means something. Because we're talking about error. And if I just, instead of squaring the differences, if the differences can be positive and negative, minimizing the sum of the sum of the differences, I can always make that 0. And that's no good. That means there are too many lines that will work for our data. Now, if we're trying to deceive our audience, maybe this is what we'll go with. But we want to minimize the sum of the squared differences. Now it's going to be harder to deceive our audience, because now we will be looking for one line that fits best according to this, according to these rules. That makes sense? You've got to establish the rules before you start doing things with any kind of authority. Like if you win a street race, but the other guy wasn't racing you, then you didn't win anything. There wasn't anything going on. You didn't establish the rules ahead of time. By the way, don't street race. That's just juvenile. And you shouldn't do it. You'll get someone killed, and it'll be your fault. The biggest problem is that street racers maybe get themselves killed, so we don't have anyone to punish, except the next person that comes along and tries to do it. You know what I mean? Don't do that. It's irresponsible. So that's the concept behind least squares. We want to find a line and look at the square differences of the line. What we want to do in chapter 6 is just expand this concept. Instead of just data points in R2, what if we want to build a plane that best fits a bunch of data? We can do the same thing. We want to expand this from points in R2 to points in R3, or points in R4, and so on. Now, once we get this concept, now we can expand to more dimensions. Now we just need to expand things to higher dimensions. We'll look at points. We'll look at a plane and a point not on that plane. And we will want to know how close is that to the plane or the three-dimensional space. We're still looking for differences. We're going to square them differences and minimize it. Any questions? Not exactly a deep dive into least square problems, but it's it's an important technique for evaluating any model that you make. You look at all the data that you have, you say, I think this model fits the data. It's like, of all models of that type, is it the least squares model? Any questions? Comments? Snide remarks? This is why everybody should take a statistics class. even though statistics classes might not be required for your particular major, like if you're an engineer or something like that. There are also practical reasons you should take a statistics class. If you have taken calculus and linear algebra, a good way to make money is by tutoring people that are struggling in algebra or struggling in calculus or struggling in a statistics class. If you've never had a stats class, you won't be able to help them. But if you take a stats class, you've now expanded your portfolio of tutoring to include a lot more students than it did before. So I saw a significant increase in the number of students that I was able to tutor once I took a statistics class and put myself on the board as an available tutor for statistics. Just went right up. Any questions? All right, I'm going to pause the video here with our very shallow dip our toe into the pool of least squares problems, and we'll go over any other questions you might have.